My report is about adhesion. I will tell a little more than Professor Popov about our experiments which we make to investigate different adhesive properties of materials. Okay, on the first slide you can see different applications in principle of adhesion in nature. In nature, several plants use adhesion to attach to the surfaces, and with using of this adhesive mechanism, these plants can grow up to 30 meters. You can see this house. And adhesion use also different bacteria to attach themselves to our organs. It's also important to know these adhesive properties to produce different medicaments to make this adhesion lower. And cells in our organs are connected also due to adhesion. Also adhesion is widely used, for example, for different technological processes, as usual, painting, soldering, and adhesion use also several animals, as here on the picture, the gecko, to move along the walls with different angles. And we developed for investigation one kind of tribometer. You can see here 3 pictures. It's a concept, then 3D model, and it was realized in real equipment. And we can consider here normal motion with precessive linear stage 1 and tangential motion with linear stage 2. And here the schema of the experiment. It's contact between steel hard indenter and rubber layer. We use transparent rubber, and with camera from the bottom of the contact we can observe what happens in the contact. And this device has very good precision. We can move our indenter with accuracy up to plus minus 0.2 micrometer. It's lower than the size of bacteria. The size of bacteria in this picture is 2 micrometers. With using of the stage, you can in principle cut the bacteria on several pieces. And also we use rotation stage 8. On this video, you can see the example of using of our equipment as usual plotter. We just made it for demonstration. You can write something or paint something in the usual Cartesian coordinates, x and y, and program saves this. And after this, you need to calculate this in polar coordinates because we use rotation stage. With the rotation stage, we move our rubber layer, and together with rotation stage, we have all 3 coordinates. Normal motion, tangential motion, and also third coordinate. And here you can see that to repeat this word, we need all action of all 3 stages. This linear stage and rotation stage. And of course, the equipment work now in polar coordinates. And it means that with our device, we can use it for investigation of normal contacts, we can use it as linear tribometer, we can use it as rotation tribometer, and we can apply it for investigation of contacts with very different loading scenario, with any loading scenario, and not only for adhesion, just for usual contacts. If we have in upper point 1 body, lower second body, we can move it in different trajectories. It's universal tribometer in principle. And here is this difference between the classical GKR theory and the experiment. In experiment, you have also different adhesive curves at indentation and detachment. In GKR theory, after propagation of the contact in point A to the point B with negative normal force and with further indentation, we will have always one curve. If we change the motion direction of the motion of indenter, but in real experiment, if we change the motion of direction of motion, we have also secondary adhesive hysteresis, and due to this hysteresis, we have also additional dissipation of mechanical energy. This indentation, the action of adhesion is very low. We observed also at this first contact point negative normal force, but it's very small normal force, and at detachment you can see this normal force, this adhesive force is much lower, negative values due to adhesion. And here is also video. Is a video of one experiment for normal contact. It's indentation and in detachment. We save the pictures of contact area, and due to analyzing possibility of analyzing of these pictures, we can calculate the contact area value. And you can see here these hysteresis in the dependencies, force, indentation depth, and area of the contact, and indentation depth also. In the slide, you can see the comparison between experiments and theory. On the right, it's similar dependence, the same dependence, but on the right, it's a large area. And curves 1 and 2, it's experiment. Curves 3 and 4, it's JKR theory with account of thickness of the layer. And points 5, it's simulation with boundary elements method. It is an experiment. Upper 3 plots is experiment, lower 3 plots it's simulation of indentation if this indenter has non-homogeneous distribution of surface energy. You can see it here. This non-homogeneity was produced with action of ferrum fluor 3 about 1 minute on the surface, on the steel surface. It's chemical treatment, and after this chemical treatment we have observed increasing of surface energy up to 20 times. It's also spherical indenter. In usual case with homogeneous properties you have circle form of the contact, but now it's something different. And in principle, in simulation with boundary elements methods, we got the same results. What is here interesting, in each next indentation cycle, we have observed lower and lower adhesive properties, lower and lower this adhesive force during detachment because of contamination of contacting surfaces. You can see here there is a big difference between first and second cycle. There are differences between each cycles, but the biggest difference is between first and second cycles of indentation. And in simulation, we just use different values of surface energy to repeat experimentally observed behavior of our contact system. And we prepared this distribution of surface energy also based on experimental picture. So we can calculate with our simulation different sizes, different forms of this distribution of surface energy. And next experiments on the surface of rubber, we had sand hard particles. And also indentation was performed. Firstly, we have increasing of normal force without direct contact between rubber and indenter. And after some time, there are direct contact. It can be very important applications for rubber seals, for example. And it also can be simulated. We have got very good coincides between experiments and simulation, I think, including the form of the curves. And you can see here jump-like detachment of the rubber. It is always jump-like detachment, but if you have chemical non-homogeneities or particles or very big roughness, this sizes of rubber at this jump-like detachment are more pronounced. Okay, the next slide. It's also location of the particles in the contact between rubber and layer, but as a particles we have used here steel balls with diameter of 1 millimeter. And if we have steel balls, we know that diameter is a constant of the steel balls. and we can prepare this system for simulations more precise in comparison with sand particles, because sand particles have different shapes, different geometrical shapes, and we prepared our picture for simulation based on a picture of the contact from the bottom. We did not measure this with microscope, for example, shape of these particles. And you can see here also some difference between experiment and simulation, but we have observed in principle also the same curve. For example, it's interesting at indentation depths. At the indentation phase, firstly, the adhesion is very weak, but we have increasing of contact stiffness. This force and indentation depth relationship is non-linear, firstly. After this, we have observed linear dependence. It's constant stiffness, and then after appearance of the first contact between rubber and elastomer direct contact, we have observed also non-linear dependence and then also linear dependence. So we got different contact properties on different stage, different contact stiffnesses. It's also several indentation depths and several indentation cycles and several indentation cycles in simulation. And here I have shown the direct contact, this dependence of area of contact as indentation depth. It's direct contact between rubber and indenter, and you can see that we have direct contact if we have indentation depth approximately 0.75 in experiment and in simulations also. In principle, it's approximately the same contact area, these contact shapes. And here is also experiment with periodical motion of indenter. We performed indentation to the maximum indentation depth of 0.15 millimeter. Then we performed detachment, but not to full destruction of the contact. And then we changed once again direction of motion of our indenter. It's a cyclic motion of indenter in JKR. In principle, in this case, we did not observe any hysteresis. And if we did not observe hysteresis, there is no dissipation of the mechanical energy. But in real experiment, in this dependence force and indentation depth, you can see this hysteresis. And in principle, it looks like a cycle in thermodynamics. If we have the hysteresis, the area of this hysteresis is a dissipation of mechanical energy due to adhesion. There is no in classical theories JKR such kind of hysteresis. And down all these three panels below, you can observe the results of simulation, but not in boundary limits method. It was simulated within the framework of method of dimensionality reduction. But for half space, and in experiment we used layers show bigger thickness. Because of this, in experiment we have bigger values of the force, of the normal force. It's possible to use MDR, this method of dimensionality reduction, or boundary LMS method for thin layers, and we can obtain approximately the same curves with the same values of forces. But it was not the aim of this work. The aim was to show what happens in such a system. And the last slide, it's tangential motion of indenter. Here, after indentation depth to some critical value, we performed motion of the indenter with very small velocity, 1 micrometer per second. You can see here the black spots. Black spots are areas of indenter after chemical treatment, which show much bigger adhesive work, adhesive strengths. It's a chemically non-homogeneous system. And you can observe here very difficult and I would say very strange processes in the contact. It's something like elastic waves propagation, and the velocity of these elastic waves, we have bigger velocities at the areas with bigger adhesive strengths, because at these areas we need apply much more tangential stresses before beginning the sliding. And you can see here dependences. This red dependence, it's a normal force. Normal force is constant because we have the constant indentation depths. And tangential force, in principle, you can see that we performed firstly indentation in normal direction. Tangential force was 0, then increasing of this tangential force, then something like stiction spike, and then approximately constant value of tangential force. And we can calculate here also dependence of friction coefficient. Friction coefficient has no physical sense. In this case, it can be very big for adhesive system. And it was the last slide. Thank you for your attention.